Okay, let's get started for the afternoon session. So, well, from here, for my lecture, we are just starting the cosmic reionization stories. So, the aim of this lecture is for you to understand the result of the cosmic reionization history constrained by the optical to near-infrared observations and CMB plus 21 centimeter observations. And this is the advanced notice. So the question to you this time is, what is the role of Lyman-alpha mission, LAE, observations in the reionization history studies? What is the advantage and disadvantage of the Lyman-alpha emitter approach? Okay, so let's start cosmic reionization. This is the schematic form of the cosmic history from the Big Bang to today. And as you know, after the recombination of the universe, the universe is filled with the neutral medium. And on the other hand, if you look at the today's universe, you know, the medium, intergalactic medium, is the totally ionized. So this is the UV spectrum of the 3C273 at redshift 1.6, and this is the Lyman-alpha, and this is our Milky Way Lyman-alpha absorption. So in other words, between this quasar and us, you know, we do not see the significant absorption. In other words, the media is quite transparent for Lyman-alpha, and it is the very good contrast with the quasar spectra of the redshift around 4. You know, you see the significant absorption features. So you know, the IgM as the present epoch of the universe is the well ionized. So then you know the neutral media and ionized media. So sometime between this recombination epoch and our epoch, there's the reionization event, and as I will tell you that the ionized reionization took place before redshift greater than 6. That is found by the quasar studies, spectrum studies. So this animation shows the numerical simulation results recovering the cosmic reionization. The size of the box corresponds to about a few tens of megaparsecs, so cosmological simulation, and the green and orange media are the neutral hydrogen and ionized hydrogen. And once the galaxies form, these galaxies are shown with the blue dots. Well, you know, they emit the ionizing photons by the star-forming activities, and then they make the ionized bubbles or the cosmic H2 bubbles, and then these bubbles get big and they merge, and then the universe is ionized. So this is the basic picture of the cosmic reionization that people have, and now, but of course, you know, it is not clear that this picture is correct, and of course, the galaxies, whether galaxies are real, ionizing source, major ionizing source or not. So you may worry that, we talked about the galaxy formation a lot, and this time you are listening totally different topic. But well, actually, the cosmic reionization itself is galaxy formation. As you know, as I said, the galaxies are emitting ionizing photons by star formation activities, and the universe is ionized. And then, within the ionized bubbles, the UV background radiation is strong. So the small halos, the dwarf galaxy star forming activities is suppressed by such a UV background radiation. So in this way, the galaxy formation and the cosmic reionization is related. Well, of course, many of the ionizing photons are produced in galaxies. So maybe you can say, this process is the kind of cosmological scale feedback. So, emitting the ionizing photons by galaxies, then such photons are coming to the other galaxies, and their star-forming activities are suppressed. And then the question of the cosmic reionization is the history of the reionization. In other words, you can quantify the neutral hydrogen fraction, neutral hydrogen fraction XH1, which is defined by the neutral hydrogen density divided by the entire hydrogen density. Or another popular quantity is the ionized fraction, which you use the QH2. So this QH2 is just the 1 minus XH1. So okay, so both quantities are used. So then the question is that how XH1 evolves as a function of the redshift. And well, of course, if you can observe this, kind of volume fraction of the ionized, IgM and the neutral IgM like this way, then it is very easy. But in fact, it is very, very difficult to quantify the ionized fraction and the ionized fraction and the neutral fraction by observations, because the intergalactic medium is very, very diffuse. So with the current technology, you cannot identify the emission from the ionized bubbles, as well as the neutral medium, even using the 21 centimeter observations. So then you may worry that, so how you can do that? Of course, if you have the very bright background source, such like quasars, you can identify diffuse neutral hydrogen. So this is a very famous way to quantify neutral hydrogen. So using the quasar spectrum, and you can measure the observed flux, and you can predict estimate the intrinsic flux by the power law. Then you can get the optical depth of the Lyman-alpha, which is named the Gunn-Peterson optical depth. And this Gunn-Peterson optical depth is related with the neutral hydrogen fraction. So using this technique, well, you can measure the tau Gunn-Peterson optical depth, and then you can derive neutral hydrogen fraction. So this is a quite famous result of the Saas-Fee found, showing the average neutral hydrogen fraction derived by this Gunn-Peterson optical depth. And as you can see, at around redshift 6, there's a possible sudden increase of the neutral hydrogen fraction. So that's why the people think that this is the end of the cosmic reionization, because the neutral hydrogen fraction is rising rapidly. And but well, this technique has a limitation because, as you can see in this equation, this factor is so large because the cross section of the neutral H1 Lyman-alpha is so large. So if you have the very small fraction of the neutral hydrogen, like the 0.01%, you have the pretty large tau, then your quasar spectrum is pretty easily dumped, and you cannot get the meaningful information from it. So it is the great technique, but maybe you can use this technique up to redshift 6 when the universe doesn't have much the neutral hydrogen. So the next technique is to use the CMB. CMB is another great background light, and to identify the ionized media or free electrons between the CMB and us. Well, CMB is extremely bright, actually, like you can see the 400 photons per cc in the universe. So it's the signal is very strong. So And this time, what you can measure is not the neutral hydrogen, but ionized gas or free electrons, because the CMB photons are traveling through us. There are, if the free electrons exist, then these photons interact with the electrons via Thomson scattering. And so such a Thomson scattering makes the polarization signals in the CMB, and also it smears out the temperature fluctuations of the original CMB. So using these pieces of information, you can derive the optical depth of the Thomson scattering in the CMB photons. And then once you determine the optical depth, then for naively, optical depth doesn't have the spatial information. So just one dimension. So what people do is to simply assume the reionization took place instantaneously. Then you can resolve this equation, this integral easily, like with this format. So then you can plug in the tau, and then you can obtain the redshift of the instantaneous reionization. And the current best estimate of the tau is 0.066 from the Planck 2015, and the corresponding instantaneous reionization epoch is the redshift 8.8. But this technique still has the problem, because there's no time resolution, as I said. So having the result of the Gunn-Peterson optical depth and Thomson scattering optical depth, there are some constraints on the history of the cosmic reionization or XH1 evolution. And now the cosmic reionization completed at redshift around 6, and there's a lower limit of the cosmic reionization from tau instantaneous model. So, but between redshift around 6 to 10, there are no meaningful observational constraints, and there are several competing theoretical models of the cosmic history, cosmic reionization history exist, so you cannot distinguish them. So then what you need is you want to have the observational constraints in this epoch, redshift 6 to 10. So what you can do is to use the Lyman-alpha damping ring absorption, as you hear a lot about it in the Xavier's talk. Well, Lyman-alpha damping ring absorption is pretty good this time, because the cross section of the damping ring is quite weak, low, compared with the entire absorption. So about the 5 orders of magnitude, weaker than the entire, hydrogen Lyman-alpha absorption. So, the problem of the hydrogen absorption is too sensitive, but this, tail of the Lyman-alpha absorption is very useful to prove the high neutral hydrogen regime. So then, of course, you need some background light to measure this damping ring absorption given by the neutral IgM. So there are 3 sources of the background: GRB, QSO, and galaxy. So let's look at these 3 source results. One is the gamma ray burst GRBs. This shows the redshift 6.3 gamma ray burst spectrum, and as you can see, it shows the nice damping ring absorption around here. And and then you can derive the neutral hydrogen fraction of IgM. However, the GRB should have the host, DRA absorption given by the host galaxy. So, from this, you can just get the upper limit of the neutral hydrogen fraction of the 17% at redshift 6.3. And then you may think that what about the higher redshift gamma ray burst? Yes, there exists the redshift 8.2 gamma ray burst. That is the highest redshift one. But as you can see, the spectrum is extremely poor to identify damping wing absorption. So you can't use this. So maybe we should wait for the next bright GRB for to constrain the reionization with the damping wing absorption. And the second background source is the quasars. And this is the highest redshift quasar of at redshift 7.1. And well, you can make the fit of the damping wing absorption feature. And well, it is the quasar is quite complicated, having the proximity effect and so on. But well, the various studies identify that probably this feature indicates the neutral hydrogen fraction should be about greater than 10% at redshift 7.1. And the third source is finally our objects, Lyman-alpha emitters. So well, galaxies are very faint, so you cannot use the damping wing absorption in continuum. But of course, this can be applied to the Lyman-alpha emission lines. Then if you have the strong damping wing absorption, then Lyman-alpha luminosity get dim. So in this way, you can use the Lyman-alpha emission lines as a proof of the cosmic reionization. And this shows the Lyman-alpha luminosity function from redshift 5.7 to 7.3. And as you can see, from redshift around 5.7 or 6.6, there's a strong decrease in Lyman-alpha luminosity function. But you may worry that this could be made by the evolution of the cosmic star formation history. If you go to higher redshift, you have less cosmic star formation rate density. But so to quantify this, you can integrate this Lyman-alpha luminosity function to get the Lyman-alpha luminosity density. And the evolution of the Lyman-alpha luminosity density is shown with the red points here. And as you can see, from redshift 6.6 to 7.3, you have the significant drop. And this is in great contrast with the UV luminosity density evolution. So from redshift around 4 to 8, at least up to redshift 8, it shows the very smooth decrease of the UV luminosity density, which is roughly proportional to the cosmic star formation rate density. So there's no indication of the strong sudden drop of the cosmic star formation rate density, but here you can find significant drop, especially around redshift 7. So the similar result is obtained from the similar techniques. So as I told you yesterday, so people are measuring the Lyman-alpha emitting galaxy fraction. So as a function of redshift using the continuum selected dropout galaxies. And then I said from redshift 4 to 6, Lyman-alpha emitting galaxy fraction is increasing, and at redshift around 6, the Lyman-alpha emitting fraction is about 50%. It's great. But if you look at this fraction beyond redshift 7, it's dropping and towards redshift 8. So this is another piece of the evidence that probably there is the significant increase of the neutral hydrogen of IgM beyond redshift 6. And then you may worry that, well, you said not many Lyman-alpha emitters should be found because their Lyman-alpha emission lines are absorbed by the neutral IgM. Why do you have the Lyman-alpha emission lines at redshift, say, 7.7 or 8.7? Yes, it is a very difficult question. However, as you can see, there's a strong drop in the Lyman-alpha emitting galaxy fraction. So these populations are quite special objects. So people observe hundreds of such a continuum selected object with the Keck Mossfire, but mostly they fail. But some lucky people identified the such a, well, not lucky, but well, there are some great techniques I know, but well, these are very rare sources. So, but still they exist. So how Lyman-alpha emission lines can escape from such a neutral media? So this is the very interesting astrophysical question, and well, some theorists try to answer this thing after the wrong. No, sorry, never mind. Okay, okay. So this is the well, the theoretical predictions of the Lyman-alpha escape fraction of the galaxies at redshift around, I forget, 9 or 10, and well, for some bright sources are clustered and making bigger H2 bubbles, cosmic H2 bubbles, so which are bigger than the other average cosmic bubbles in the given redshift or epoch. So that helps, that big, clustered galaxies and making their big, ionized bubble help the Lyman-alpha emission line escape from the highly neutral media. So this model predicted about 10% of the Lyman-alpha can escape even in the at the heart of the cosmic reionization epoch. So to summarize the cosmic reionization history, I show the neutral hydrogen fraction as a function of redshift and having the many constraints given by the quasar dumping ring, CMB, and GRB quasar Lyman-alpha emitter dumping ring absorption lines. As you can see, still there are many upper limits, lower limits, and large error results. So well, there are many constraints, but still the constraints are weak to distinguish the several competing reionization models, and also it is not clear that the reionization is suddenly happens or sharp process or extended process. So maybe other constraints are needed to understand more about cosmic reionization history. So here then of course people think that, well, 21 centimeter observations are quite promising. That is true. The idea of the 21 centimeter observation is to identify hyperfine structure line of 21 centimeter, which is made by the spin flip of the neutral hydrogen atom, I mean the proton and electron. And well, this is very famous astronomical probe. And this, the 21 centimeter is redshifted, highly redshifted, and you can observe this line as the about 100 megahertz frequency regime. And many experiments are being made, including GMRT, Paper, Loafer, and MWA so far. And before we look at the constraints from the 21 centimeter observations, let's look at some theoretical predictions. So the key quantity of the 21 centimeter signal is the spin temperature, which is defined with the well, this statistical mechanics thing. And also, this spin temperatures can be compared with the CMB temperature and kinetic temperature of gas. And this right panel shows the temperature as a function of the redshift, and starting from around redshift 200. And this blue line shows the CMB temperature, so it's decreasing by 1 plus Z, as you know. And the spin temperature first at redshift around 200, it has the collisions of the atoms, so it follows the kinetic temperature. And then at around redshift 70, the universe, the matter density becomes quite low, so the spin temperature differed from the kinetic temperature. But at around redshift 20, the Lyman-alpha emission is coming from the object, and it redistributes the hyperfine state. Then it comes down, and then the other, X-ray heating sources and many heating sources comes out. Astronomical sources comes out at below redshift 15. So then the spin temperature and kinetic temperatures goes up. So what do you measure by the 21 centimeter observation is the brightness temperature, which is proportional to the spin temperature minus the CMB temperature. And okay, so this shows the brightness temperature, expected the brightness temperature. And as I said, as you saw, this diagram, in the early epoch of the universe, the spin temperature is below CMB temperature. So the brightness temperature is the minus. So in other words, these signals are observed as the absorption. And then after the reionization starts, then the spin temperature goes up beyond in a positive. Beyond CMB temperature, so you can identify the 21 centimeter signal as an emission. So then of course, the current epoch is current technology is now trying to identify this, emission of the 21 centimeter signal up to redshift around 15 or so, and then this. Left panel shows the current constraints of the 21 centimeter power spectrum given by the many 21 centimeter observations. And like paper and upgraded paper result for the cyan and GMRT and MWA. All of them are 2 sigma upper limits. And you can compare this with the expected 21 centimeter power spectrum for the 50% of the neutral hydrogen fraction. So as you can see, present upper limits about the 1 to 2 orders of magnitude higher than the expected signal. So we need to do a lot to try to identify the real signal. And also such a more sensitive instruments, and of course the most challenging part of 21 centimeter observation is how to model the Earth ionosphere, which is the great foreground source that doesn't allow you to push the detection limit. So, LOFA people are working on very seriously on it. So I summarize the lecture 5, cosmic reionization. What I have explained is the constraints on the cosmic reionization history, or XH1 evolution. And I show the Gunn-Peterson test, CMB, Lyman-alpha damping ring for the GRB quasars and Lyman-alpha emitters. And definitive thing that we can say now is the epoch of reionization is greater than 6. And of course there are some constraints, but still constraints are not strong enough. And the open question is that the cosmic reionization history, whether the history is quite sharp or extended reionization history. Okay, so then let's move on to the discussion and the presentation. So the question to you is what is the role of the LA observations in the reionization history studies? What is the advantages and disadvantages of Lyman-alpha emitter approach? Okay, please start. So we have 30 seconds more, so please wrap up your discussion. Okay. Oh. Wow, that's amazing. Okay, let's start the other presentation. So any volunteers? Yes, please, Haruka, go ahead. Okay. Use the other microphone.
If my voice is loud. Hello, my name is Haruka Kusakabe from University of Tokyo. We discuss about disadvantage and advantage. First, disadvantage is very clear. The difficulty of observation of Lyman emitters. And advantages, we discussed two things. First, we can estimate the end of the reionization error from the highest redshift Lyman emitters. And second, some Lyman emitters trace the geometrical effect, for example, ISM or halo mass. I mean that massive halo galaxies resided in massive halo mass easily reionize first, or such kind of things. Some information maybe on the spectra of Lyman emission. That's all.
I mean, when you say it's difficult to observe Lyman-alpha emitters, you mean you're talking about high redshifts, right? I mean, yeah, because at low redshifts we already have a lot of observations. Yeah. And another thing, like we talked about, like I don't think we can talk about the other end of using Lyman-alpha emitters. Can we constrain the other end of Lyman-alpha emitters? I mean, reionization. I mean, okay, we can find out the lower, like at which redshifts it ended, but can we probe, like when did it start using Lyman-alpha emitters? Because we don't have too many Lyman-alpha emitters at very high redshifts. So, I mean, that's what. So basically we can, is it that we can use Lyman-alpha emitters only to constrain the low redshift part, right? The end. Yeah, low redshift end of reionization.
Not the very beginning. But, okay.
No, one thing that we thought, one thing that we thought as an advantage actually is, I mean, it's true that you have a few LAEs at redshift like 8 or 9, but still that's deeper than where you can currently get with quasars, for example. So, and you're already entering a redshift range that should be more constraining for the reionization epoch, as you showed in those plots earlier. So that's actually also an advantage, we thought. No? I don't know.
So anything else?
Okay.
Do you have any comments? No. So, well, so any more, how do you say, volunteers from you? Yeah.
Comment, or it's more like a question probably. But so the thing we were discussing is it would be very nice if you could actually use the Lyman-alpha line as a tracer for the Lyman continuum. But I think this is probably quite difficult as Lyman-alpha relies on so many other effects. So if you observe Lyman-alpha emitters, then you cannot really probe the reionization itself.
So maybe I think your how to say discussion result is somehow the Lyman-alpha emitters are very dependent on the galaxy properties, ISM, everything. So you cannot easily distinguish between the effect of the galaxy evolution and neutral hydrogen, neutral IgM evolution. So I definitely agree with you. And but well, that Lyman-alpha is as you saw in the sharp drops of the Lyman-alpha luminosity density and also Lyman-alpha emitting galaxy fraction. So that gives the the information is degenerate, but this is another important proof of both galaxy formation and reionization. So what we can do for observers, maybe you can get the precise measurements, of the Lyman-alpha properties of the galaxies, and then that can be the strong constraint on the reionization and galaxy formation. And as I said, galaxy, cosmic reionization is galaxy formation. So in this sense, it's perfect. Okay, so I think the time is running out. So let's stop here. So thank you.